Right, okay, so we'll be talking about certificates for large tree width in this lecture and maybe also later on again. What do I mean by that? Well, if a graph has low tree width, then that's easy to convince you of. I just show you a tree decomposition. You have to verify that indeed it is a tree decomposition, but that's not too hard. And then you just look at how big is the largest bag. And then I can, if that has size at most k, then you know that the tree width is certainly less than k. But how do I convince you that the tree width of a graph is large? So I'd have to show you that there does not exist a tree decomposition whose bags are all at most a certain size, like k, and that's not so easy, right? So we can't go through all the possible tree decompositions, all the possible trees and ways of coming up with bags indexed by these, by the nodes of those trees and so on. So that's quite a bit harder. And so it's interesting to have certificates by which I can persuade you that a certain graph does not have a tree decomposition of low width. And I'm going to show you the main one today and prove what's sometimes called a duality theorem, that the tree width of a graph is large if and only if such a certificate of large tree width exists in that graph. Technically, this is important also for our big goal to prove the quasi-ordering of the finite graphs by the minor relation, and that is because we've already seen that I've already told you that the graphs of bounded tree width are well quasi-ordered, a bit like Kruskall's theorem, and in fact the proof is a bit like Kruskall's theorem. So for every given fixed k, the class of all graphs of tree width less than k is not so hard to be shown to be well quasi-ordered. So in the proof of the theorem that all finite graphs are well quasi-ordered, we would like to say, well, either they have bounded tree width or some infinite sequence of graphs in which we want to find a good pair. Either they have bounded tree width, in which case we're fine, or they don't. And if they don't, we want to get something in return, something we can work with, and such a certificate is a good start. So here's an example. A bramble in a graph. So do you know what brambles are? Brambles are like thickets with lots of thorns and so on, like raspberry brambles and things you don't want to go into and risk getting scratched all over. So a bramble, a thorny thicket, is a collection of connected sets of vertices pairwise touching. And what does touching mean? Well, it means that either that any two sets either meet or have an edge between them. Okay, that's what it means for a collection of sets, a set of sets of vertices to touch. It means that any two of them either meet or have an edge going from one to the other. Right, so that's a bramble, and a cover of a bramble B is a set of vertices that hit every set in the bramble. meeting every set in the Bramble. So for example, here, if we had a few more sets, maybe not like that, maybe more like this, and suppose this was our Bramble, then we could cover it by, so how many sets do we have? 1, 2, 3, 4, 5, 6 sets. They're pairwise touching, I didn't draw all the edges. Right, 6 sets, but it's enough to choose 1, 2, 3, 4, 5. Do I really only have 6 sets? 1, 2, 3, 4, 5, 6, 7 sets. Okay, 7 sets, but I can cover them with 5 vertices. Right? I have found a cover, a set of vertices meeting every set of the Bramble, and the orange set of vertices is such a cover. And the order of a Bramble is the minimum size of a cover. So the order of this Bramble here is probably 5. I haven't shown you that. I have shown you that it is at most 5 because I've produced a cover consisting of only 5 vertices. Maybe there's a cover of 4 vertices, but I doubt it. So that's the notion of a Bramble. And here's a nice example. Here's a K by K grid. And the crosses in this grid, the connected sets that contain 1 column and 1 row form a Bramble. So these are connected sets, right? So the vertices of the grid are where the lines cross. The lines themselves are the edges, right? So that's the graph. And such a cross is a connected set of vertices. And clearly every 2 crosses meet, right? So I'll take another cross. It meets the green cross. So every 2 crosses touch, they even meet. And how can I cover all the crosses economically? I don't want to use many vertices to cover them with. Well, I could, for example, take an entire row. Right, so that would be a cover by K vertices, and that would hit every cross, because every cross has to contain a column. So K is fine. And I can't do with fewer than K. So if I have fewer than K vertices, I'm going to miss a column, and I'm going to miss a row, because I have K columns and K rows. So if I have K minus something vertices, I can't hit all the columns, and I can't hit all the rows, and those any column and any row that I miss form a cross that I haven't covered. Okay, so the crosses form a Bramble of order Okay. Right, and up there is the main theorem for today. It says that the existence of a Bramble of large order is a certificate for large tree width, and in fact, it's a tight certificate. So the implication goes both ways. If the tree width is at least k, then there is a Bramble of large order witnessing that. There's a Bramble of order bigger than k, and if there is such a Bramble, then the tree width cannot be smaller. So the forward implication is the hard implication, which I'm going to prove to you for most of the time today. And the back implication is easy, and it's nice. Right, so that's what I want to show you now. If there is a tree decomposition whose bags all have size at most k, so tree width at less than k, if there exists a tree decomposition whose bags all have size at most k, all of them, then there's no Bramble of order bigger than k. So every Bramble can be covered by at most k vertices. And in fact, I'm going to show you that every Bramble can be covered not by just any old set of at most k vertices, but by one of the bags of this particular tree decomposition. And how do we do that? Well, much in the way in which we showed that complete subgraphs sit in a bag of any tree decomposition, and that is if we have a separation of the graph, and now we consider any Bramble. So Bramble sets are, what are they, green. So if this intersection here covers the Bramble, then we're going to be fine because we're going to be considering the separations that this tree decomposition induces. So remember, those are the separations corresponding to the adhesion sets. All the bags on one side, union of them, versus all the union of all the bags on the other side. Those separations we're going to be considering, and I'm just drawing one here. So we'll be happy if such an adhesion set covers our given Bramble. Remember, we have any given Bramble. I want to show you that some part covers that Bramble. If an adhesion set covers it, we're happy. If not, the adhesion set is going to miss a Bramble set, and since Bramble sets are connected, they can't sort of miss the adhesion set and then still meet both sides. So any Bramble set has to lie on one side or the other. But if one Bramble set lies on the right, you can't have any Bramble set on the left because they have to touch, right? And they can't intersect because the adhesion set, by assumption, doesn't hit these particular sets, and there's no edge like that either. So if one Bramble set sits squarely on the right, then any Bramble set that misses the adhesion set will also lie on the right. Okay, in that case, we can, as previously, put an arrow on this separation from left to right. And that's what we're going to do here. So if we have the underlying tree, if there is no adhesion set hitting our hypothetical Bramble, then we can put an arrow on every edge of that decomposition tree. The edges correspond to these separations that I've indicated here. And whenever we order the edges of a tree, we'll get to a sink, to a node of the tree, to which all its incident edges point. And then we know of these three separations that there is no Bramble set here, there's no Bramble set here, and there's no Bramble set here. Right, so every Bramble set meets this bag in the middle. So that bag is a cover of our Bramble, and we have shown that for any tree decomposition, in any Bramble, there exists a bag that covers the Bramble. Right? I'm not talking about sizes at this point. Every tree decomposition, every Bramble, there exists a part of that tree decomposition that hits the Bramble, that covers the Bramble. So let me rephrase this theorem in a bad way, and then tell you why it's bad, or why it's a popular way to phrase it, but it doesn't capture its full strength, that theorem. Okay, so we have seen that these are the natural numbers. Okay. Cover sizes of Brambles and widths. No, let's not say widths. Let's say maximum bag sizes of tree decompositions. I have shown, or our particular proof here, which finds a bag in any tree decomposition that covers a given Bramble, shows that the smallest cover sizes of Brambles are no bigger than the largest sizes of tree decompositions. Take any tree decomposition, any Bramble, you'll find a bag that covers it, so the smallest cover has size no bigger than the largest bag. Okay, so that's what we've just shown in particular. And the theorem is often stated as saying that equality is attained. There exists a k for any given graph, and there exists a k such that some tree decomposition has largest bag size k, and some Bramble has smallest cover size k. Right? But that isn't the whole truth. That doesn't capture this quite. Why not? Because this just asserts that there exists a bramble and there exists a smallest cover that is no bigger than K, and there exists a tree decomposition whose largest bag is no smaller than K, and there exists a tree decomposition whose largest bag has size no bigger than K, but this largest bag could be any set of vertices, and this smallest cover could be any set of vertices. All this tells us that they have the same size. And our proof actually shows us that there exists one set of vertices that does both jobs at once. Right? So it's a stronger theorem. This is a structural duality. And you could rephrase that theorem in a more structural way by saying that there exists a triple, say, a tree decomposition, a bramble, and a bag in that tree decomposition, where this bag is a cover of that bramble and a minimum cover of that bramble and a maximum bag in that size of that particular tree decomposition. Right, that witness both these at once. Okay, questions about that so far? If not, then you risk that I'll launch into that proof. So your time to ask questions? No? Okay. Okay. So let me wipe the board. And we'll prove the forward implication there. Sorry, I hinted at this fact, but I didn't spell it out. This strong duality is what you know from Menger's theorem, right? Menger's theorem also is sometimes stated as saying that the biggest size of a set of disjoint paths from A to B equals the smallest size of a separator, an AB separator, and the strong version says we can actually find one set of disjoint paths, and we can find a separator that has one vertex on each of these paths. And then those two together witness that the other is optimal. And you have the same situation here with this particular VT that witnesses that both the tree decomposition and the bramble are optimal. So you can't have a tree decomposition of smaller size because then an even smaller bag would cover the bramble, which we're assuming is not the case. And you can't have a bramble that needs a bigger cover because we can actually cover it by this particular set VT. Right, so let's prove the forward implication. We'll assume that the tree width of a given graph G is big, and we'll find a bramble of order bigger than K. That's K. Okay, so we need the notion of a good tree decomposition. Right, you can just about read that now, I think. Yeah. So a good tree decomposition is one, well, let me draw it, and then talk about it. So this refers to our particular K there. K is now fixed. And a good tree decomposition is a weakening of the tree decomposition of the type we would actually like. What we would like is a tree decomposition of with less than K, whose bags have size at most K. Right? Those are the nice tree decomposition, those of width less than K, so bag size at most K. But they might not exist, and in fact, we're now assuming they don't exist. And a good tree decomposition is a weakening that always exists. And what is the weakening? The weakening says that non-leaf parts must not contain more than K vertices. Right? Tree width or width of the decomposition less than K says no part must contain more than K vertices. We're weakening that to requiring that the non-leaf parts are small, have at most K vertices. The leaf parts are allowed to have bigger than more than K vertices. And there's a second requirement that seems redundant unless you think about it really hard. The second requirement is that there exists a part that has at most K vertices. So that automatically exists unless all the nodes of the tree are leaves. Well, can that happen? Yes, it can happen. That's your tree. Right, and both are leaves. And then one of them has to have size at most K, one of the bags. Okay, so this is sort of nearly redundant, but it only bites for this particular tree. Okay, and so why do they always exist? Well, we could always take the tree decomposition for tree equals K2. So the two-node tree whose two bags are the empty set and the entire vertex set. So, of course, they look like this. Right? And that would be allowed. So that's a valid tree decomposition, not a particularly useful one normally, but that is a valid tree decomposition that is good. It does have a bag whose size is at most K, because K is at least 0, and every non-leaf is made of green cheese. Okay, so these good tree decompositions always exist, and that's important for the proof that comes. Right, now we need the notion of a petal. So a petal is the set of vertices not in the adhesion set of a leaf bag of big size. So we're assuming this particular leaf bag has size bigger than k, and only then can we talk about petals. And if we have such a leaf bag whose size is bigger than k, then the petal is the set of all vertices of G that are not in the adhesion set. So that's a petal. And now I can reveal the last little bit. Namely, I can tell you what the bramble is that we're going to find. We have to find a bramble of order bigger than k. Right? And I'm going to show you that bramble now. Okay, let B, curly B, be the set of petals of good tree decompositions, such that blah, blah, blah. What does that mean? You consider all possible good tree decompositions, such as this trivial one, but any others too. And you look at every good tree decomposition, by the way, has a petal. Why is that? Well, it has a leaf bag of size bigger than k. If it didn't, then all its bags would have size at most k, in which case the width of that tree decomposition would be less than k, which it isn't by assumption. So every tree decomposition, every good tree decomposition has a petal, and we take the set of all petals that occur in all good tree decompositions, and we haven't a clue what those are. We just know some exist, such that they represent, our collection represents all the good tree decompositions. So every good tree decomposition has a petal in our particular set, curly B. That's condition 1. And condition 2 is that B is closed upwards. So if we have a position, call it X, in our collection B, and that's a subset of some X prime that's a petal of some other good tree decomposition, then this X prime also has to be in B. Okay? So B is any set, and in fact not any set, but a minimal set with respect to inclusion, a minimal set of petals of good tree decompositions that represent the petals of every good tree decomposition. So for every good tree decomposition, there's a petal in our collection B. And whenever we have a petal in our tree decomposition and some superset is a petal in some other good tree decomposition, that's also going to be in B. Okay, that's B. You don't have to remember it, that's why it's there. I'll be referring back to this lots of times. And now, our bramble is not B, but B prime, the connected sets in B. Right? Remember, bramble sets have to be connected, and so the sets in B, the petals aren't necessarily connected. You never know what those are, but we just take the connected ones. Okay? So we have to show now that B prime, that thing here, is a bramble of order bigger than k. And before I show you that it's a bramble, I'll show you that it has order bigger than k. So what does that mean? It means that we cannot cover it by at most k vertices. So let me show you that. So we can't cover B prime by any set Z of most k vertices. Why not? Here it is, at most k vertices. Well, look at the components of G minus that set Z. So C1, C2, C whatever, n. Right. Let's look at those components. This is a good tree decomposition. No, not this. Here's a good tree decomposition. How do I draw that? I take this as a bag. And then, so the edges here, right? And any component plus z as a bag. Okay, so our tree decomposition has as its tree a 3 star in this case, or an n star if we have n components, with z the central bag, and each of the leaf bags is a component plus z and all the edges between them. All right, so that's a tree decomposition. All the edges are covered. There's no edge from here directly to there by definition of these components. So that's a tree decomposition. It's also a good tree decomposition because it has a bag of size at most k, and every non-leaf bag, and that's only this, also has size at most k. So it's a good tree decomposition. Right, but the CI include a petal. Why is that? It's a good tree decomposition, but we know that the tree width is at least k, so it must have a bag of size bigger than k. The central bag doesn't have size bigger than k, so it must be one of the component bags, say this one. So this has size bigger than k, right? And what's its leaf? The attachment set, sorry, the adhesion set is Z. So this part here contains Z, but Z is also its adhesion set. Okay, so the petal for this bag, which I'm assuming has size bigger than K, is precisely that component. That component is connected, and it's a petal of a good tree decomposition, and B prime, and Z doesn't cover it. So we need to show that this is, in fact, in B prime. Well, it's connected, so all we have to show is that it's in B. But B satisfies this, that every good tree decomposition has a petal in B. So, in fact, I wouldn't have had to reprove that one of these sizes has, that one of these leaf bags has size bigger than K, because our assumption about B hands us such a petal. So every good tree decomposition, and this is a good tree decomposition by assumption, has a petal in B. So if this is in B, then if this petal is in B, then it's in fact in B prime because it's connected and Z isn't covering it. Okay, so that shows that our B prime, if indeed it is a Bramble, which I haven't shown, cannot be a Bramble of order at most k. So its order will be bigger than k if indeed it is a Bramble. Okay, So let's prove that it is indeed a Bramble. So what do we have to prove? The sets are connected. So all we have to show is that the sets in B prime pairwise touch. Still to show. Sets in B prime touch. Right? Okay. So suppose suppose not. Suppose there are x and y in B prime, and in fact, I'm going to show you that any sets in B touch. Right? Suppose there are x and y in B that don't touch. And I'll be spending the next half hour showing you a contradiction. We can choose x, y to be minimal in B, y. Well, we can choose them as minimal non-touching sets in B if we're assuming that B contains two non-touching sets. Then we can say, okay, let's take a pair that is minimal with this property, and those are going to be minimal, in fact, in B altogether, because if you take a subset, that's not going to touch the other set either. So if we have two non-touching sets, then taking a minimal element of curly B inside each of them will still have a pair of non-touching sets. So they're minimal in B, not with respect to some property, but they're minimal in B full stop. Okay. Now, then if we take them out of B, what do we get? We get sets that are smaller than curly B. Curly B was minimal with all this. So these are still going to be sets of petals of good tree decompositions because they're a subset of curly B, but they're not going to satisfy 1 and 2. Now, they're still going to satisfy 2 because they're minimal. So 2 says that curly B is closed up. If we delete a minimal element, then the rest is still closed up. Right? If we have any element that remains that's still in here, and take a superset of that, well, that superset used to be in B, but it can't be X, because X is minimal. It's not a superset of some other set. So these two things still satisfy 2, but by minimality of curly B, they can't satisfy both 2 and 1, so they violate 1. Okay, so 1 says that every good tree decomposition has a petal in that set. So there exists a tree decomposition T1, V1, and T2, V2, whose only petals in B are X, Y. Right? There's a tree decomposition that violates one for this. So a good tree decomposition, it is a good tree decomposition that has no petal in here. But we know it has a petal in B. So it's a good tree decomposition whose only petal is X. Whose only petal in B is X. And similarly, there's another tree decomposition whose only petal in B is Y. Of course, they may have other petals, but the only petals in B are X and Y. And those we shall work with. Those true tree decompositions. So let me draw them. We have T1, V1 here. Something like that. And we have T2, V2 here, and they have I used blue, so let me use blue again, or maybe blue and green. Only petals in B are X and Y respectively. Right, so the set X is a set of vertices of G. That is the only petal of one tree decomposition, and Y is a set of vertices of G. That is the only petal in B, always, in B of the other good tree decompositions. They're both good tree decompositions. Okay. And X and Y don't touch. Right, so they don't meet, and there's no edge from X to Y. Okay. This is a tree decomposition of G. That's a tree decomposition of G. So I've drawn them disjoint. But of course, they're not at all disjoint. There's the same vertex set of G covered by both. Except these two sets are really disjoint. But all this, so this Y is somewhere in here. And the X is somewhere in there. But nicely disjoint from Y, and Y is nicely disjoint from X. In fact, it's not only disjoint from X, it's disjoint from X and its neighbors, right? Because they don't touch. So Y is not going to include a neighbor of X, of big X. And let's assume that the tree decomposition does not have any vertices in the bag Vx, that's a little x, and that's a little y, that needn't be in this bag. So a vertex that doesn't lie in the petal big X and is not adjacent to anything in the petal big X doesn't really need to lie in the part. So we're assuming it doesn't. Okay, so the part Vx consists of the petal, big X, and the vertices that need to be in the adhesion set. And which are those? Those are the neighbors of big X. Okay. And so this is the neighborhood of X, and this is the neighborhood of Y, these adhesion sets. And then we know that Y is not only disjoint from X itself, but it's disjoint from X and the adhesion set of V little x, because any vertex of Y in there would be a neighbor of big X, and so Y would touch X, which it doesn't. Right, so that's quite a few properties already. And there's one more property which we'll be using later. So X is not going to be a subset of any petal of this tree decomposition, and Y is not going to be a subset of any petal of this tree decomposition. So let me justify that. Why is that true? If X was in a petal, this X was a subset of a petal of this tree decomposition. Suppose it is. That tree decomposition is a good tree decomposition. Then that petal of which it is a subset would be in curly B, because curly B is closed up. But this tree decomposition doesn't have any petals in curly B other than Y. So this superset here, this petal of the right-hand tree decomposition that contains X, would actually be Y. But surely X is not a subset of Y. It doesn't even meet Y. And similarly, in the other case. Right, so we're going to use that later, right at the end of the proof. that will come up again. Okay. Don't ask me how this proof is found. Right? I mean, it's really a masterpiece, I think, as is the original proof. So this proof that I'm showing you is due to Frédéric Mazoit, who was here in Hamburg as a visitor many years ago when he proved this. And so I was so fascinated by that proof that I included it in the book. I previously had a slightly shortened version of the original proof by Paul Seymour and Robin Thomas, who first proved that theorem in the book. So you can find the original proof, or a shorter version of the original proof, in editions prior to the 5th edition, and this book in the 5th, and a better write-up of it in the text that you have from the 6th edition. Okay, so that's what we're going to work with. And now I need one more property. And that is what we're going to show from now on. We're going to combine these two tree decompositions to make one tree decomposition which has a particular property. And that's as follows. We'll show there exists a good tree decomposition TV such that two things happen. All the petals are subsets of petals of those two. And the second is that X and Y are not petals. Of that tree decomposition. So basically, what we're going to do is take these two tree decompositions and identify X and Y. So make these two trees, which we're assuming to be disjoint. The trees are disjoint, not the bags. The trees are disjoint. So G is decomposed in one way, G is decomposed, the same G is decomposed in another way, but the decomposition trees are just disjoint by decree. We're making them disjoint, and then we're combining them, we're going to combine them into one tree where X and Y are merged into one node R, little r, and then all the other bags are essentially preserved, not quite, but are essentially the same. And then that's going to be a tree decomposition of G that basically covers it twice, right? But we don't mind that. It's a totally weird tree decomposition. It covers G here, and it again covers it there. But it will have this property, and this property star will finish our proof. So let me prove that it does. So if star holds, so if we find a tree decomposition just with these properties, I told you that how roughly we're going to obtain it, but you don't need that now. So if we just have a good tree decomposition with these properties, the petals each petal is contained in a petal of one of these. And X and Y are not petals. Then that will give us a contradiction because it won't have any petals in B, in curly B. So why is it not going to have any petals in B? Well, consider a petal that is in B. It is included in a petal of one of these. By being since B is closed up, upwards, this other petal that contains our petal in B would also be in B. But the petals of these things aren't in B, except for X and Y. So our petal here would be contained in X or Y. But it can't be in B and contained in X and Y because X and Y are minimal in B without being equal to X or B. But they're not equal to X or B, X or Y, right? So if we have star, then we'll have completed the proof. We'll have a contradiction. Okay, that's the overview. This is a good sort of time to ask questions. No? Okay. So all the information that's here has been repeated on the left, I think. In particular, that X and Y don't touch. So let's prove star. We have to construct a tree decomposition, but we need some footwork before. So let's look at the following. There exists a separation as follows. There's A, and there's B, and there's at most k vertices in the intersection, such that X is entirely on the left, so in A minus B, and Y is entirely on the right in B minus A. So, and we'll choose, well, why does that exist? Well, we could, for example, take as the separator the neighbors of X. So here, the neighborhood of X is a subset of this neighboring bag, so that has at most k vertices, certainly, because that's a petal. So that is either in an inner node of tree, in which case the bag has size at most k, or if the tree is k2, then it's the only, then it must have size at most k as well, because that bag doesn't, right? So this entire bag has at most k vertices, so in particular the adhesion set there has at most k vertices. And that's all I'm asking here. And if we look at the separation here, X on the right, sorry, now right and left are interchanged, so X on the right and everything else on the left. So that is a separation that has X on one side and Y on the other side, and neither of them meets the separator, right? Like here. Okay, so that exists. Call the separator S, and we choose it with S at most as small as possible, this separator as small as possible. Okay. Then, by Menger, there are paths indexed by the vertices in S. From S to the neighbors of X. So the neighbors of X might include vertices in S. X itself not. But the neighbors might, but that's fine. So we apply Menger to the neighborhood of X, which is still in A, and to S, which is in A, and we apply Menger in the graph that A induces in G. And we'll find paths, disjoint paths from S to the neighbors of X. How many? Well, one for every element of X, S. And why is that? Well, if not, we'd have a smaller separator by Menger. If we didn't have cardinality S many paths, we'd have a smaller separator, but that smaller separator would still have X squarely to the left of it, right? So this separator might include vertices here, but not vertices of X. Then that would be, and Y would be to the right of that separator, and that would contradict the choice of AB with S as small as possible. So there are these paths. And similarly, there are paths Q little s, and the little s's run through the elements of big S. Jointly linking S to n of x and n of y. Okay. Right. And now I'm going to modify these tree decompositions just a little bit before we can merge them. And the reason I want to do that is that in order to merge two tree decompositions of the same graph, you need a node of the decomposition tree whose parts are identical to tree decomposition. So suppose, just to use this picture, suppose this bag was identical to that bag here. Then we could just identify these nodes and call this same bag the bag of the identified node. And then the axioms for tree decompositions would just hold as they did before, right? So every edge is covered by some bag. Well, it already used to be covered here. It also used to be covered there. So it's covered by two bags, at least, right? Well, or by this identified bag. And a vertex that lies in two bags lies in every bag on the way, well, where are the two bags? It could be the central bag and some bag here, then it would lie in every bag here, and they're copied to the new tree decomposition, so that would still be fine. Okay, so merging two tree decompositions is trivial if each of them has a leaf bag, that is the same as a leaf bag of the other. Okay, but that isn't the case here, right? So big X and big Y are the opposite of being identical. They're disjoint. So we're going to get from this tree decomposition a tree decomposition that uses this picture here, in which S is going to be a leaf bag. So now careful, this tree decomposition is going to give us a tree decomposition of the right-hand side here with S a leaf bag. And this tree decomposition is going to give us a tree decomposition of the left side here, also with S as a leaf bag. And then we'll stick them together. So let me define those true tree decompositions. This gives rise to a tree decomposition of the subgraph of G induced by B. And how do we do that? Well, you know already, I've shown you how to find tree decompositions induced on subgraphs. And that is you just intersect every bag with the vertices in the subgraph. So we could happily take from this tree decomposition of G a tree decomposition of B, of B, just by intersecting every bag with B. Don't try to see them. Don't try to see where these bags are and so on. It's completely, these two pictures are, you have to have a mind split and think about both pictures at once. But don't try to merge them. Well, you're a genius if you can, I can't. Right? So, still, let's bear in mind the credentials of each of the two pictures at the same time. This tree decomposition will give us a tree decomposition of the subgraph that B induces easily, just by intersecting every bag with B. But in fact, we want to induce a tree decomposition not just on this subgraph, but on a graph with some additional edges on S. And which edges of S shall we add? Well, whenever two paths of this path system here have an edge between them, then I want to add this edge. And how do we do that formally? Well, formally, we take this tree decomposition and apply it to the following minor of G. We first delete everything on the left in A minus B outside the paths P, S. Delete everything outside the paths. And then contract every path to S. Each path gets contracted all the way to its end vertex in S. Right, and the edges between these paths then become edges on S. Right? So formally, of course, this minor would have branch sets, the vertices of each of the paths. But the branch sets have representatives in S, in big S. So we may as well think of each branch set as actually a vertex in S. Every branch set has a unique vertex in S, and every vertex in S is in a unique branch set, because if the branch sets are these paths. Right, so that's the minor to which we apply this tree decomposition, which consists of essentially the subgraph that B induces in G plus additional edges when are little s and little s prime made adjacent if there's a path from P, little s to P, little s prime. Okay, we do the same on the other side. So this was T1 V1. So T1 V1 induces a tree decomposition with the same tree, T1, V1 prime on G induced by B plus edges on S, those edges on S. And similarly, T2, V2 induces a tree decomposition with the same tree T2 and slightly augmented bags V2 prime. So the, what are the bags? The bags here are, for a bag here, V little t. The little t is an index here as well. So we have a V little t prime. What is the V little t prime? It is Vt intersect B. Sorry about the B. This is the B from the separation here. It's nothing to do with the Bramble. V intersect B, let me put brackets just to be quite clear, together with these little s's, such that Vt, the original Vt, this one here, meets the path Ps. Right, so if that was Vt, so we're talking about this upper case here, not about that case. If this was Vt, maybe only this little s was in Vt, so we need these two s's as well, because in our Vt prime, because this Vt meets the corresponding paths, right? And we want these red edges there as well, which this doesn't reflect, but I've told you. Okay. So this isn't quite right. This is on GB plus some vertices from S and similarly here, plus vertices and edges on S. Okay. Right, so Right, these are now tree decompositions which we can merge, and we're going to do that. This is the required tree decomposition here. T is going to be T1, disjoint union with T2, with X, Y identified to a new tree, to a new node. Right, so if we had little x and in T1 and little y in T2, then the new tree will be the union of the disjoint union of the T2s, the Ti, but then with these leaves, x and y identified into one new vertex R, little r. And little r is not going to be a leaf of that tree, T. Why is that not going to be a leaf? Well, we need that such other nodes exist here, and that other nodes exist here. So why do they exist? Well, if they didn't exist, then v little x would be the only bag of T of the first tree decomposition, but it can't be the only bag of the first tree decomposition because y has to be covered. So that exists. And similarly, a neighbor there exists. So this is not going to be a leaf. Of T. Okay. And what is curly V? Well, we can just write it as the VT, so T is in T. So how are the VT defined? I want to call this VT, and that, of course, is a VT1. Yeah. Right, so the bags here, sorry, the bags of this tree decomposition are called VT up 1. The bags of this tree decomposition are called VT up 2. And the modified such bags are simply called VT, so that I can use them here. I haven't used the abbreviation VT before, luckily. So these VT are defined in this way. So that's just the definition for this case. There's a similar definition for that case, but they'll also be called V little t, except these little t's in this case will be elements of T2. Now, luckily, when the little t is x, what is VT? So what is V little x? Well, V little x is what happens to this bag here in the modified tree decomposition. This is Vx1. What happens to this bag, Vx1? Here's the bag Vx1. that's going to be S. And that is because v little x1 meets every ps, because all the ps reach the neighborhood of x. So they reach a vertex in vx up 1. So all the little s's here are going to be put in v little x because v little x1 meets ps. Right? N of x may have some other vertices as well, but that's immaterial here. So for every little s, the appropriate path reaches the neighborhood of x, so it reaches v little x, 1. And for that reason, this little s is going to be put in this set here, so it's going to be an element of Vt, and that's the only, these are the only elements, so this is going to be all of S. There's nothing here because V1 doesn't intersect B anywhere outside S. So X doesn't intersect B at all. The neighbors of X may intersect B, but only in S. Okay, so Vx is S, and V little y is also S. So V little y is obtained from this corresponding definition of the VTs for this line here, where those 1s are going to be 2s. Exactly the same argument. In the case of x and y, little vr is going to be S as well. Okay? Right. So, now all that remains to do is show that this decomposition satisfies star. And I'll just see that I've run out of time. So I've shown you already that this is going to be a tree decomposition of G, because we have two tree decompositions now, these modified ones, and they have leaf bags that coincide, so they can be merged as we did. The VT, these new parts here, are no bigger than the original parts, VT1 or VT2, from which they came. Why not? Well, we added some new vertices. So VT here had some vertices of S added. VT1 had some vertices of S added when we turned it into VT. But we only added vertices for earlier vertices from VT1, namely those on the corresponding path. So either these corresponding path vertices were already in S, in which case we didn't add anything, or they were not in S, in which case we didn't take them anymore, because, yeah, they're not in here. So we deleted those and instead replaced them with those, so they didn't get any bigger. That's important because now we want a good tree decomposition, so the VT for non-leaf parts still have to be small, have to have at most k vertices, and the non-leaf part of this tree decomposition is either R, in which case the size is the size of S, which is at most k, that's fine, and the other non-leaf parts are non-leaf parts of the two tree decompositions which we invested here, so that's fine. So it is a good tree decomposition, And what we have to show now is that every petal of the new tree decomposition here is included in a petal of one of the older tree decompositions. And X and Y themselves are not petals. Yeah. And that takes a moment. Let me just say that this is where this property is suddenly needed. So it's a little complicated. Just read it up in the text, and it's just checking, but this particular condition will suddenly be used there and hasn't been used before. Right.